Hello, everyone. Welcome to the MicroSim GP Amric session. We'll look at the Amric solver in general, that what it is and why we chose to use the Amric solver in the MicroSim. So myself, Nasir Attar, and I'm from CDAC Pune, and we developed the Amric solver for MicroSim. So starting with the motivation, what is Amrics? So there should be some sort of motivation for us to use Amrics. So let's say you have a 2D equation and you want to simulate it. Now you can either run it on a server, on a cluster, or you can either run it on a laptop, right? And then you can visualize it probably, that how the diffusion is happening. But the thing is, architectures these days are very diverse. So if you develop considering one set of architecture, you have to, and if you want to migrate it to another, it comes at a significant cost. So there is a modification cost associated to it. There's also, again, the effort that you put in. So it's twice the effort, right? So you want something. So definitely this thing is challenging. I mean, how you can write a code that can run on every machine. So we have a solution to that. So let's say I write my code in Amric software framework. So what it does is, it hides the architecture details from you. So you can definitely, you can easily port your code across multiple architectures. Right? So yeah, that's there. We have solved the problem, but now we have to understand what is there in Amrics so that we can easily use it, right? So don't worry, I won't dive into much theory or details of Amrics, but we'll just try to understand the flow of the code, and we'll see how we can use Amrics to our benefit. Okay. So to begin with the overview, we'll first explore what is Amrics. Then we'll look at a few functionalities that make it very different. Then we'll see the problem that we are solving, and followed by results and the performances that we have generated using it. Okay. That way we can reach to the final Amrics flag. So yeah, before beginning the session, I like to tell you that Amrics is, the full form of Amrics is Adaptive Mesh Refinement Exascale. So you can either use a single level solver or a multi-level solver in Amrics. So right now I'm going to demonstrate a single level solver. Later, Akash will show you how a multi-level solver looks like. So we'll just look at a few basic functionalities of Amrics. Yeah, so this is the basic flow of the code of a single level solver. This is a pseudocode. Now, I don't expect you to remember all of these details, but as we proceed, as we visualize what is happening in the code, you can see that we're checking a certain number of boxes, and then you can understand that what is happening where in the code. Okay. So to begin with the problem, if I want to solve a problem, the first thing that I want to know is, what is my coordinate system? So we first define a coordinate system. Let's say we're beginning with the Cartesian coordinates. Okay. The next thing is we define the domain, right? What our computational domain is, the number of cells in X direction, the number of cells in Y direction, followed by a real box. Now, if I want to simulate it in a real domain, I have to map these number of cells to a real box, right? So right now here I have 10 cells, and if I map it to 0 to 1, so it will make my dx to be 0.1. So now we have the next is boundary condition. So once we define the boundary condition, we have, the problem definition is there. The basic is there. So you can see that these first three boxes we've ticked. Okay, the first one, it's okay. It's just reading the input parameters from the input file. So I haven't covered it here, but that's what it does. So now that we have the domain, we'd like to parallelize it. So to make it parallel, we'll just cut it into 4 different parts, right? So why we want to make it parallel? Definitely because we want to make it faster. Okay, we'll just offload these to multiple processors, and then we can, solve the problem in a faster way. Yeah. So there are different boxes. So let's say on a single level, the collection of these boxes is held in the box array. Okay, so you can see in the pseudocode there is a statement written as box array BA. So that's what this is for. Okay, so now that we have split the boxes, we want to map them onto different processors. Okay, so let's say if I map the first one to rank 0, the next to rank 1, then rank 2 and rank 3. Now I've followed a certain set pattern here. Okay, if you want, you have the capability, I mean, you have the option to change the mapping pattern as well. Okay, it's depending how you want to do it. So let's say we've just mapped it in a inverse Z order. So here you can see that you've defined the domain. The max size max grid is something. Let's say you want to split the domain, but you want to tell the Amrex that I don't want the box size to exceed a certain limit. So let's say here we have 0 to 100 number of cells. I'll say that I don't want to go beyond, I don't want a certain box to go beyond 50 number of cells. So what it does is it will chop the boxes in less than that. And it finds the optimal way to do it so that each processor gets even amount of load. Yes, so we've done with the distribution mapping. Now we want to solve the problem, but first we want to store our data somewhere, right? So we need so we want to store our data somewhere. So we need a multi-dimensional array for that, right? So we'll just use multifab. So we have rows, we have columns, and this is definitely the partition that we have. Okay. So now if you remember that we've mapped our boxes to different processors. Okay. So what this yellow thing that you can see surrounding a processor is the ghost cell. Okay. And we have the valid box. Now, what the ghost cell does is it's for the communication. Let's say I'm at the boundary. I hope you can see the cursor. Yeah. Let's say I'm at the boundary and I want the data at the next cell. But I mean, it's not there, right? The box is split. So if I want the data from the other neighboring rank, what I do is I copy that data into the ghost cell. So the derivative that I want to compute, so the number of ghost cells depend on that. Okay. So if I want I plus 1, I'll just add one layer of ghost cell. If I want I plus 2, I'll add 2 layers of ghost cell. Okay. So I'll just copy that. It will be stored in the ghost cell and later it is updated. Okay. Yeah. So now we know how a multifab basically works. I'll explain it later.
So if you remember what all he said, I'm going to write this, you will look for those words in Amrex manual, right? Box array. E is capital?
Yes.
Box array. Then he said geometry. Real box was there?
Yes. Capital B.
Real box was there. Fine. Right? How do we define a domain? You have a domain. You write this coordinates. You write this coordinate. It's done. We are going to, so this works on the blocks, layers of blocks. When we go to adaptive mesh also, we use the blocks. So you have given this coordinate, you have given this coordinate. You are done. Fine. Now what he does, he's splitting it into 4. Okay. Now the split one, I'm going to write in some other color because this requires this. This is again there. The ones which are there. So I'm going to represent this by 2. The ones which is split up again here. So how this domain is going to be split? It is something like this. We drew this for you. Okay. This was there. So you require this. Again you require this. Again you require this. and this was max dim, he said. This was max dim. So had it been 16 by 16 and max dim was 4, this is what is seen. Just imagine it. So now if this were 0, 0, where are you here? 1, 2. So, okay, there is an issue there with what do you call it? Centered ones and half centered. So let's number this block with this block centered like this. So this is goes by, this block is 0, 0. So if this is mean where they are, we are here 3, 3, right? 0, 1, 2, 3, 3, 0, 1, 2, 3. It's the same here. Where does this end? 0, 0. This ends in 0, 3. So this begins in 0, 3. Once you understand this, you're through. Where are we here? Because it was 16. It's not 16. It was 8 by 8, right? 8 by 8. Correct? So this would be 3, 7. Correct me if I'm wrong. It's basic coordinate geometry, right? So you will see again here, where are we? This is not, okay, this is 7. So this is 7, 7. What was your? This was 3, 3. This one, 0, 3. If I'm making mistake,
3, 0.
Stop me.
3, 0.
3, 0. No,
No,
7, 0.
no, the other one.
7, 3. Which one?
Middle, yeah.
This is 3, 0. Correct. 3, 0. So if you understand that, you have understood the game. So now what happens? Whatever he called as box. So I've told boxes. Initially, the box was there, the original computational domain. But now you know how to discretize it. But you have, unless you map it to the geometry, you don't have delta x, delta y. It's meaningless. It's just giving slicing. So only when you combine this, the discretization through max dim and geometry, you have defined the problem. Your delta x and delta y is defined. And now, once you have divided this, these forms, these one form the group box size, and all of your thing is going to happen. Then what happens? Now you have 4 domains. So he said rank 0, rank 1, rank 2, rank 3. This is the way you label yourself. You have a roll number. So 4 processes are there. So this is grouped into something called virtual topology like this 4 of 2 by 2 virtual topology. But this here you call it as distribution mapping. So if you're familiar with MPI, you would have heard of this term virtual topology. Whatever was doing that machinery translates it into distributed mapping. The distributed mapping is again tied to this box array. Am I right?
Yeah.
We are operating over that. And your domain is defined through delta x and geometry. So you have discretized the problem. Now you have done this piece goes by the name of domain decomposition. And now I'm just going to jump gears, switch gears and tell you he was trying to do this operator. Correct? What is the discrete form of this? This turns out to be a stencil like this. If you really use finite difference, all that, this will be left neighbor I plus 1j, I minus 1j, I j plus 1, I j minus 1. Fine? Do you see it? It goes by the name of 5-point stencil. The point and its 4 neighbors. And now think of it, if you want to update here, you need this, you need this. This is here. This is here. Whereas these two are in somebody else's pocket. So I need permissions, I need protocols, how to handle it. It's the same here. Look at here. Or it's going to be there, this wherever you had a cut, you consider it here. So this has neighbors here, so that is doable. This is there, this is there. This has to come from here. So the strategy is you keep a layer wherever the interface was there. That is what you call as posts. Okay, and now you have, these are called subdomains, and you can do a computation independently only if you do have this layer of ghost. So this was a boundary, this was a boundary. So you know the boundary conditions, whereas this layer you require, this piece you require here. Which was this? It was this. This. So you maintain a copy. So this has the boundary value stored there. So the same can be replicated. And the whole thing, say if you are going to have a 16 by 16, then you have dividing like this. How would it look like? This, shoot them out, all have to be with their burst. And if you have periodic boundary condition, it folds up here. You have it here. For your problem, the same is there for this virtual topology. Periodic, non-periodic, all that can be done. So that gives you a mechanism. So what we are doing is, if you look at this, goes by the name of parallel programming. So here, this goes by the name of domain decomposition, which is used for multiple processor implementation. But think of it, you are sitting on a quad-core system. You could have done it. Whatever this called as processes, this label, so I would call it thread ID. Like this is easy, data parallel. With shared memory, no give and take and all that. But this problem doesn't scale, this model doesn't scale. And through 4-core system done. What if I want to divide it by 16 by 16? I can do oversubscription. Effectively, it's going to slow down it. So if I have to integrate 4 such boxes, I can do it. This is the mechanism. You understand? Right? So this, whatever was, if you look at MPI text, this will be called as virtual topology. The operating thing is distributed mapping here. And that binds you this with this. And you need to store data. Only then you will do computation. Okay? So you need this data to be stored. You need this layers. That depends on your operator form. Because this operator can be even this star, stencil, all that. So it depends on. So the subdomain data includes even the layers. Okay? Union of all the layers is multipath. Okay? I stop it. It's going to take. Any questions before we proceed?
Fab is array box, Fortran based array box.
Array box.
Array box. Fortran.
Oh, Fortran array. We have still not forgotten. So I should sit here. Yeah. Yeah, please go ahead. So if you have issues, please stop us. Once you know the notation, we'll go through the code.
Yeah.
We're going to do the code. So you'll see the keyword list of the things which you will get to look at the manual.
Can you see my screen?
Yeah.
There.
It's exactly what he said. I have drawn it for you. Only thing is I did the storytelling.
Yeah, so now we have the ghost cells and the box that is there at the center. It's known as valid box. Okay, that is our actual domain. Okay.
Okay, maybe I should read that. The valid box is the thing which gives the ownership. If it is mapped to 0, it will work in the region of it, the points associated with its valid box.
So now if I want to generate the plot file from this, I'll remove the ghost cell, add up, stitch the boxes, and then generate a plot file. Okay, that's how it's done. And that's what you can see, right? Single level plot file at the bottom here. Okay, this at the center is our iteration space. So we'll have a look at it in detail. So now that we know the basic flow of the AMVIX code,
Okay, maybe
we'll
stop there. Get emphasis on MF.
Yeah, I'll do it. Yeah. Okay. So yeah, basically even I can do it here. So the boxes that he has shown you, okay, everything is executed parallelly within this MF iter box. So MF iter stands for multifab iterator. Exactly. So now that you have the boxes, the computations are being done parallelly. Yes, yes.
Takes care of data parallel part.
Yeah, yeah. That's why I've used valid box there.
There it is on a kernel. So it's a tricky part to understand. But the point is, whatever you want to do in a very exhaustive way here, that is handled through that. And when you say MF iter, it is valid boxes for that particular one. It's the multifab iterator. So you have to scan it anyway. That you don't have anything else to do. You have to scan.
Okay, so basically, if ID is valid, it's this is the valid worker for that.
Because
Yeah.
you know, they not work on the other ones.
Yes.
Then for it will go false.
It runs through all the loops, finds out the valid and writes the
Runs it, yeah.
False. So it knows where to, what is it?
Yes. So we'll look at the functionalities that are at the center of Amrex solvers. There's abstraction and there's portability. That's what makes your life easy. So to begin with the abstraction, you can remember that we had ghost cells and we had valid boxes. So if you look at this part in the code, so MF is our multifab. Okay, multifab. If I use fill boundary, so I mean, it just makes your life easy. You don't have to worry if it's built on CPU, if it's built on GPU, anything is there. It just fills the ghost cells for you. So let's say on CPU, it is handled using MPI. Now, if you want to move to GPU, okay, the wrapping, the data wrapping that is being done, that the transfer from valid box to ghost cells, and again from ghost cell to valid box, it is done. It is done on GPU kernels are launched if you're using GPU, so it makes it even faster. So I mean, you don't have to worry about anything. You just have to write mf.fill boundary, and all the ghost cells are filled.
In fact, it takes care of the physical boundary also. In this problem, that physical boundary.
Yeah. So
what was the exception?
Where?
It takes care of 3 of it. Right?
No, it only takes care of physical boundary in periodic cases. Yeah, only periodic cases. Yeah. Others are we have to fill. Yeah.
It has a nice mechanism on Neumann also. Myself and Abhishek sat to and read the whole class for it. Was a boundary condition.
The ghost cell is able to become values, right? Wanted to have
Yeah, I can give the number of ghost cells, but depends on what the derivative I mean, what index I need. I plus 1, I plus 2. Yeah. Multi-layer ghost cells we can have. Yes. So now in the iteration space, let's say you can see this parallel for, right? So if I ran it on CPU, okay, it will just run like a normal loop, okay, where the code is mapped to a certain box and everything is fine. Now I can use, let's say if I zoom in on a specific box, okay, let's say there are 36 points in those boxes. I can even use styling or cache blocking and use OpenMP to spawn threads and make the simulation even faster. Okay. Now the other thing that I can do is for that small box in which there were 36 points, I can launch GPU threads itself. Okay. Now I want all these functionalities to be there, but I don't want to change the code. I don't want to invest in changing the code. Okay. So this parallel for does it for you. Okay. Only for OpenMP, above this for loop, you need a pragma. But apart from that, the code structure is the same. So this Amrex GPU device, when launched on GPU, it launches GPU kernels. When built with CPU, it runs like a normal loop. So I mean, it's just there. It won't affect your performance or anything. So that gives you the portability across multiple architectures or multiple types of machines that you need. So we've explored Amrex. We've seen the functionalities that it holds. Okay. Now we'll look at the problem. Now you've already gone over this multiple times, so I don't want to emphasize much on this, but we all something that I want to add is we've also added the elastic part into these codes, and we also have the chemical potential equation where we have anti-trapping current as well.
Multiple component multi-fab support.
Yeah, it was covered, so that's why. Yeah, it was covered the other day. Abhik sir covered, so
No.
like extensions from binary to
multi-component aspect of multi-fab.
Multi-component aspect. Oh yeah.
To store data.
Yeah.
That makes life easy.
Yeah. So the multifab that you have, let's say you can have, if you're solving 3D problem, okay. So you have rows, you have I, J, K index, okay. Now, if I want a multifab that is built on similar box array and similar distribution mapping, but I want one more component of it, okay. Let's say I'm storing mu or I'm storing phi, okay. So I want two components, but they're both built on same box array and same distribution mapping. So what can I do? Rather than creating another box array and going through the same process again, I can just increase the number of components in my multifab. Okay. So that way I can have a multifab that is built on same box array, same distribution mapping, and multiple components. Basically. Yeah.
Does the structure of array or area of structure?
What do you mean?
Like mu1 and mu2 are together, or there's a mu1 array and mu2 array?
mu1 and mu2 together.
Together, right?
Yeah. Yeah, so now we've looked at the problem that we were solving. It's the grand potential model. We'll look at a few results that we've generated using these codes. So I'd like to show you the aluminum zinc alloy. During the tutorials for the hands-on session of GPMPI, he'll consider, Akash will dig. Yeah. Okay. So there's the chemical potential update, and this is the phi update. So there's a pool of liquid and the dendrite is growing. We also have a 3D capability for dendritic simulations. Yeah.
Okay, in a sense, do you write it 2D kernel and 3D kernel separately?
No, I don't do anything. I'll show you. So there's another file. It's named as GNU make file. So there are certain flags in that file. So it will take care of, you just want to write the dimensions that you use. Yeah, everything. No. They're just explicit flags that you're expressing that I want 3 dimensions or 2 dimensions. Yeah, compilation is different for 2D and 3D. Yeah, since you're making changes to the make file, the compilation has to be different.
There are
Yeah. Similar for CPU and GPU version as well. Okay, so yeah. We've also added the elasticity part. So here you can see that it's cubic. Okay. Next will so we have multiple phases into it as well, being stretched to in different directions. And the next thing, yeah, if you remember, this is the same simulation that Professor Fani Kumar showed yesterday, the Mercedes logo. I mean, these are for smaller time steps, so it didn't evolve that much. Yeah, we also have grain growth here. Okay, so right now the code that is there in the repository, so there are a few changes for us to make into that code for it to be capable of grain growth. So I haven't pushed the grain growth part as of now, but I'll add it in a few days time. So you can use it. And the best part about grain growth is you also have okay, so the area fractions are getting stored. So if you want to plot it over a period of time, that which grain size is growing, which is shrinking, you can do that. What? in 5. Okay. So let's say we
create something from parser and that
yeah. So let's say now we have simulating. Okay, we want to see how our simulations have performed. Okay, if we increase the number of computations, if we increase the number of processors. Okay, so the performance and scaling that I've done is for a 3-phase ALZN alloy. Okay, on a 1000 cross 1000 domain, and we'll see how it performs under different conditions. So yeah, this part is from the paper that I've mentioned below. Okay, it is Dr. Shenoy and Nisha Agarwal who have done it, ran it on multiple systems to check how it performs on different conditions. So the first one that you see is Skylake that has 40 number of CPUs. Then Cascade Lake has 48. AMD EPYC has 64, and EPYC Rome has 128. So I mean, you can see the trend. I mean, if I'm these are all again single node performances. So if I'm increasing the number of cores, the performance is getting better. Okay. Now these codes were tested. Yeah. So these codes were tested on Parampravega. Yeah, exactly. So now I want to see how the scaling performs. So I've done strong scaling and weak scaling. So in strong scaling, what you do is you keep the domain size fixed. You increase the number of processors. Okay. By that, what happens is per processor load is being reduced. So you can go till a point where, your communication is a bottleneck. Okay, you've reduced the problem size so much that it's not computation, it's communication that is a bottleneck. That will tell you how scalable your codes are. Okay, so now I've only reached till 480, but you can even go beyond that, and the codes scale pretty well. Okay, I mean, Ambex is pretty scalable, so that's the benefit of it. And again, in the weak scaling, what you do is in strong scaling, we reduce the computational load per processor, but here we keep the computational load per processor to be the same. Okay, so we're increasing the domain size, but we're also increasing the number of processors in a similar fashion so that the load on each processor is the same. So we just want to see that how bigger size of a problem that we can actually solve. Okay, so even here, the dashed line that you can see is the ideal behavior, and the real is following the ideal behavior. We've again performed a similar study for GPU as well. And you can see that the strong scaling and weak scaling matches pretty nicely here. So yeah, now we've explored Ambex. We've seen the functionalities that it holds. We've seen the problem that we're solving and also the results that we have generated. So, I mean, basically we have the big picture of what a single level solver looks like. Now we'll move to the multi-level solver, and we'll see how difference it makes in your simulations and the time and the computational time that it takes. So these are some references, but you can
main two concepts including adaptive mesh refinement. The one is how to generate this grid, fine grid, and another one is how to integrate the solution. Is how to integrate these numerical equations on the multiple grid, this coarse grid and fine grid. Okay, I start from the how to generate grid. Initially, how to generate grid, that is one part, and at the time of discrete time evolution, how to recreate the grid, how to generate the moving grid. Sometimes some grid part of grid is removed, some part is moved, or some part is new. But I start from grid generation. In grid generation, how to generate grid hierarchy. That is called as grid hierarchy, coarse grid and fine grids. I start. I will tell you how to generate fine grid initially. Okay. Suppose this is your base uniform grid.
Ambex calls it level 0.
That is a level 0 grid. And this is 16 cross 69. And this is the base grid is fixed all over computation. Now initially fill the base grid data with the help of initial condition. That is looks like this. Okay, box of grid is small and small. which is near around the flag cells. Because Ambrx is whole based on the block structure. And in this case, the 95% grid efficiency is there. That's why the small number of yellow cells are there.
Means level 1 is embedded into level 0. Level 2 will be embedded in 1 later.
Yes.
Color scan.
This
Oh, that is the curve.
that is different. Like it's not clearly shown.
No, what is yellow and what is pink?
Yellow is not needed for our refinement. But
Okay.
in
They don't
block structure,
See, based on the threshold, you identify the cells which are due for refinement. Rest you don't bother. Now you refine. And then there again you take a call with how many levels.
these cells are only the tag cells. But these cells are required for the switch. And these cells are required for the block structure. But according to block structure,
So this becomes that because the yellow cells are wrong.
we can reduce the computations. That's why we can list number of unnecessary cells. And here we achieve the 95% accuracy during the grid generation. And this is a grid generation algorithm on the accuracy means in the sense of computation. Here we need to do more. Suppose if I consider this cell, this grid hierarchy and this grid hierarchy, eventually I refine that block structure.
How do you quantify the percentage accuracy? Why do it? Why doing it? You don't know the actual solution. So how you can say what is accuracy?
In this case, my target is
What it means by accuracy, I think the unnecessary cells.
unnecessary computation. Reduce the unnecessary computation on the fine side. Here I created fine cell, then these are the unnecessary calculations. But here we remove that.
What it means is we cannot solve for both. What we say is that some of those cells which are marked in orange, we can't really go ahead and solve for that because they are missing more than one.
Yeah, this one is compared to right. There are more missing processes because of that. So that's a solution.
There is but this figure is a bit mistake. So you think that it be go ahead. This
Now finally, I created fine grid for only those boxes are there. Only my fine grid is this on those boxes. If I make here fine grid, no necessary, unnecessary computational cost is increases. That's why I am removing this. This is the basis of like bisection algorithm. They reduces the computational piece of fine set.
I mean, this is all dependent on the threshold value.
Yes.
So threshold is the gradient of it.
In our case, I choose a gradient.
Gradient, not the P.
Is gradient of phi. 0.1. 0.1. Greater than 0.1. Huh. 0.1.
So the only thing is, grad P is what grad P use? Grad P has a direction. So it would be a good idea to use that L squared P. So it's okay. Let's get the idea.
I calculated, write down the function for that.
Then what will it be?
I think I use square.
Red key square.
Because sometimes gradient is negative, no? But I never get negative. That's why I use square. The red color grid is my fine grid, and black color grid is my base grid. This is the constant all over computation, all over iterations. Now my next step is to fill the fine level data. Now this fine level data is filled from the base level data with the help of interpolation. There is multiple interpolation we can choose according to our accuracy, which one is more suitable to us. And the same thing we can repeat recursively for more fine grids. But in our problem, I just use 0 level and 1 level. But we can increase for second level, third level according to gradient conditions. Because if gradient is greater than 0.1, the first fine grid, gradient is greater than 0.2, then second fine grid, like this.
That interpolation function is available as part of the. Yes, an interpolation function is available as part of the
Amrex.
Amrex.
Yes. There is, I think, 6-7 interpolation functions are there. Some quadratic, linear.
So you're telling from coarse to fine.
Yes.
Right?
total.
Now my grid generation at initial is over. That is a initial time grid generation. But at the time of moving grid generation, how to handle this or how to generate that grid? The same procedure is there according to solution. But once we generate the grid, suppose this is the old grid and the new generated grid is the red one. And that is a box structure. From here, I get the data for this new generated fine grid. That is depend upon again our error estimation or gradient. So error estimation means we can take error, we can take the value of solution, or we can take the gradient.
You're talking about the LLC over or the moving grid.
No, we generate the grid.
Is parallelization happening in situ or?
That's still not obvious to us.
Sir,
Please.
no.
No. You mean how the is workload is that?
Yeah.
That's not clear to me.
So workload means
You
as per my understanding, I'm not confirmed, but as per my understanding, here I read the Nasik told initially this box patch. Now suppose I'm starting they do the calculation for the base bit, all processor according to box, different
So
boxes.
this is initially it's fine. You have four boxes.
Yes. Now here I 4 boxes. For this blue one have some data, some solution values, and new one we need to take the value.
Do you do
the common reason? Just copy from the blue red one. Those part is not common. Old grid and new grid. That part we can interpolate from course. Here the red one is a course to fine interpolation. There is course to interpolation. The only this green reason is the overlap reason. That's the it's fine.
Do you do a fine to course also?
Here.
Fine to course interpolation.
For this
See, fine copy is there. Fine to course. When you delete cell.
this is wrong.
No, course to fine is okay. Fining. Fine to course. Fine to course. See, when you're moving, no, you will have deleted cells. What do you do with fine to course?
That is the integration part. Synchronization is there.
So fine to course, you do an interpolation there?
Not interpolation, average down. That is a synchronization.
Average down. So that because that also typically requires an interpolation. Go ahead.
Okay, now currently I have fine cell For some reason, we don't have everything. That's why now my first part is code. The second part is the integrated solution. How to integrate the solution on force bit and time. In integration part, there is four part. One is integration on bit pair.
Yes.
That's part. Integration is fixed.
I just asking whether if you can give a small subcode of how you handle what is the that you do to the
I explain the code hierarchy in next part.
yes, that will be yes. Because I mean we are trying to figure out what you actually do yourself versus what is from the software library already handled by itself. This is the
What is the already also
what we are doing.
that partition I did. Now here is three parts. One is adaptive integration. Integration on bit. The last one is synchronization of left. Once we integrate, then I just try to first. Now first integration on bit. In this case, take the integration on this that's fine. But we going to take the integration on or find it, then there is both sides are but both sides are not. It is easy way to fill the both sides. The one is suppose you find it boundary, you find it both sides, some under the physical boundary, some under the old level. Some are we need to pull it from the course level. Here, finally, the green part we can just copy from the level because that part is already there. You can just copy it.
Yes.
Two types of techniques are there. One is without time subcycling, one is with time subcycling. Now, firstly, we see without time subcycling.
You're the diagram, right?
Now, the core cell dx delta x c delta x y. For find this, use the refinement. If I take in this R2, therefore delta is equal to delta x by 2. Now we can integrate both levels, force level and time level for the same time steady. Here I take time steady and force time steady.
But I don't understand RNP. From the stability condition.
No, I think you're becoming over stable
Oh,
because you're not increasing the time step twice. No, what I'm saying is finer scale, time scale, whatever you have, cursor you can increase 4 times, but not twice.
this is substitute, right?
But here the courses and like stability will measure with the courses with the type, right? If you have like
No, the point is
the courses point,
yeah.
the type 4 delta x by delta 0.5.
What is the lowest score? What is the lowest finest bit set? Yes.
The other one, we encounter
What is no such thing.
Huh? No,
no
sir.
subcycle.
You can say that for level and
Should try for that chemical potential, not for.
Yeah. Okay. Go ahead.
only I take the integration on the course level, then we can take the integration on the first level, and we can take the integration on third level. Sorry, second level. If we complete the integration, then we can synchronize the solutions. Since we use the solution on this ready for the recurrent view. That is called synchronization. The same thing we will discuss later on how to do synchronization. That is a time state. No, sorry. Now next part is
Watch out here.
time step with cycling.
So basically you do 4 time step on the level -2 for one step. The same type.
If my then my 4 delta t.
When you do this, are you exchanging information between the grids when you do this? So you were doing 4 time steps, no? On level -2.
Oh, that
Level 1.
typical loop is the synchronization part.
Yes.
So
Otherwise independent.
I see.
3 and 4. Step is there, no?
I integrate. This is my first step. Then I integrate the big one with half time. Because as per
Half
the
the
level,
level.
half the as per the level 0.
So say level 0 is gone from time. In one time it would have gone from 0 to 100. The level 1, which is the 2, would have gone there by 2 times. Right? Because
Here
it
one yes.
required 2 time step, reach the same time step as before.
Yes, that's then my next one. But here I use the 3. That's why.
Okay, you use 3 together. Then you use.
So he will complete sync that, then go. So and then again. Keep going back.
Firstly, I this is for delta t. This is for delta t by 2. This is for delta t by 4.
Yeah.
Do one more level of integration.
For reaching this level, I need to go to one more time step. Then delta 4 delta t by 4, which is equal to delta t.
So my only question is, can you do a level -2 integration independently?
Yes.
Independently, because you don't have information exchange.
Oh, no. That is
All integration is independent.
how. So that he requires gets back from finer to coarser. You do some sort of matching.
No, but you don't have that information at that time. The codes, no, at the code, you don't have information about that time on level -2.
No, but the course is not about it.
For doing -2. 2 papers would have used this and describe how they're doing it.
Amrex manual doesn't give reference to those things. It's literally software manual.
On the fine level, I completed the second step of integration. Then I need to synchronize the
Amrex itself.
result of second level to first level. Then I can integrate the first level again. Then for the second level,
And then cycle.
once we reach the delta t, then we can again synchronize for 1 to 2. And then again we need to synchronize for 0 to 1.
Okay. So the order of the synchronization matters.
Yes.
So you have to always go from fine to coarse, is it?
Yes.
So you do level 2, level 1 synchronization and do level 1, level 2, level 0 synchronization.
Yes. This order.
Yeah, this order. So you first do the finer to finest, then finer.
Because the main part of solution is captured fine level. That solution we need in coarse level.
You show the previous one. The order is very clear. How do you do that? In the previous. Let's write some numbers. So what those do?
The number is
First
first step, second step, third, fourth, fifth.
Okay.
follow that. Algorithms. Everybody is great.
This is the
Synchronized.
Just say, maybe I don't.
You're missing some element. And it's not.
Akash, is there a reason? Go to the time step count. You're counting the steps, no? Go to the previous one. I would imagine that P4 is 1, 2, and 2 is 3, and then 7, 8 is 1. Why do we not start from the final step? Because
If you want to care about it,
There we need the
we have at zero, no? At zero we have the data for all. Right? Is there a reason? It's just how it is. Yeah. Is there a difference or can you do that?
what?
You're doing the largest heat point and then going for a refinement. You can do 3 by 3 to 4 first, and then you can do 2, and then sync, and then 7, 8.
The order.
Like the other way, moving up the 3.
I think that is required for the post.
If you do that way,
This is required.
Acha.
Yeah, time interpolation will change.
So if you do that way, then the problem isn't
No,
the
because
problem
if you do one first, no,
solved.
then you have all the times available for the course for the fine interpolation.
No, I'm saying if you just find first, you have it there already.
No, you don't.
Because at 0 you have for all the last step anyway.
For when
You
you
do
do
the fine first, you have it and like 1 by 4, you have it half, you have it each time the fine which you want.
Is after we completed this, we directly jump on this.
No. Do the reverse.
4 first. 3, 4, and then we do 2 and then sync. And then 7, 8, 6. Then we go to
I think this is required for this step. Both states required to both values. Time interpolation is required.
Okay.
That's why this basis.
That means the delta T problem is not there.
Yes.
There will be different.
Now my integration part is over. Now next part is synchronization of levels. Is there is ways to synchronize level. Is two steps are required. One is the average down, and another is the reflex. If we are using finite method, then we need the reflex. But for finite method, we don't need to use the reflex. We need to take care of that according to the type of integration. For that, we can add more vertices to smooth the solution. Because at the time finite we don't have the reflex.
So we store the flux average in the boundary set.
I this average number at the final level you have high C at that side yes one. And at the final level different value of pi. If you have average down is high here, high C and the correction in course level solution. It's like this one is the final bit, the view one is the final bit. This is the post bit, final bit. One very final bit. This is the post bit, the final level. In one 4 5 levels. You can take the average 4 values.
Yeah, that's typically what's done.
That is one step. Now next is how to calculate the reflex at the boundary. Right down here. But we need why reflex is required. We need to recurrent the green level, which is nearest to fine level. This is not a fine level, but we near at the boundary.
That is that thing.
High level and coarse level. We need to find the value of that.
Yes.
Firstly, we updated that value with the help of input that is but uncorrected. We need to correct that of this place. You can just add that plus remove the plus. According to this size. Which there is 4 possibilities. They are left side or bottom. Right. But in our calculation, I not use very precise.
No, for phi it is not that necessary. But if you do the thing with mu, there it is very, very clear. Because if you do a mass conservation error during this,
So I try to do this, but I don't get how to calculate the flux.
For mu.
I tried to.
What is delta F?
Delta F is the flux difference between this and this.
So grad phi.
This is the per second phase flux. This is the
Wait. Let me understand this. So you are doing divergence Fi plus 1 minus Fi, which is F you are calling as a flux, no? So that's essentially divergence at I. I plus half, I minus half. So your divergence at I plus this divergence at J. So it's essentially summing up. So it's a divergence. So
that is my standard numerical skills.
huh?
This is a numerical skills. Standard numerical skills.
But why do you call it uncorrect? This is
Uncorrect because of
okay. This is the correct. This is what you solve, and then how do you correct it?
Need to correct this.
Or difference of flux. Cumulative. Okay. This is fine. I understand. Yeah. So basically, what you're saying is you are first computing the divergence of the flux and then computing the divergence of the error and correcting it.
So for our case, how to calculate the flux?
Same. What you have done. Go back. You have to find delta F essentially. So difference of the flux is there, no? You have to find out cumulative.
How to find that flux? Because we are using finite difference.
It doesn't matter. Finite difference and finite. You just shift yourself by this one.
Now the solution of Abu-Sheli is correct. That is the synchronization test. Now my first part that is the algorithm. Now second part, how I implemented EMR algorithm for the organization. Here I use 5 functions. The first is there is one class named EMR code. I using some function from this class which is already in Apex. Then in that same class there is some virtual functions there. That virtual functions we need to change our problem. There is 5 functions. I will explain this function later on. Then we need to write some our functions to couple this AMR code to our physics functions. The fourth one is the this is required to connect these two with our physics problem. Now I can explain which functions are required for the class. Those functions are required to generate the data hierarchy. Then
Akash, just give us a global picture. This is okay. Just give us, let's say, the code, pseudo code level, what you're essentially.
In my code, first I call the main function, which is one constructor, one is init data, another is if. The constructor is I created a new class, is inherited class of EMR basic class. That is EMR code. Now in constructor, the EMR code GP, that constructor is inherited from EMR code. There is some work which GG is EMR code, and some work which is this EMR code. What is the role of this EMR code functions? They will be EMR related parameters, and they initialize the geometry hierarchy according to our input, how much layers are required. This. and it creates the structure. Just creates from all these things are integrated. Now next, that is the implemented constructors CMR project. That's help us read the integrated parameters. Then initialize the array of multiplier according to our logic and set the boundary condition. Now next is I initialize the data.
During subcycle, the data is frozen at the place of the subcycle.
Initialize those functions which are related to
Relay in that part.
those functions which just default. We can get the parameters. Now here we start the actual EMR start. Now here I call this function. That function is used to initialize the EMR hierarchy at the beginning of the simulation. And it's called false and here is function and make to level of these two functions are the virtual functions of the EMR program. That we just need to write down as per our model. And that two functions call this function init from scratch. And this function is implemented from us. Now this function called here and this is called this is a design function calculated. This calculated the gradient and that created the grid array. Now the role of this make it new from scratch is when we have the basic this function create the higher level gates.
Just go ahead. This is idea is only.
Initialize the order parameters means they will call the now
Fill codes, get data.
fill codes.
Pseudocode.
Yes.
You read it.
Now fill codes function
ठीक है ये तो बता दिया तो ये चल आगे ये तो हो गया.
this fill codes fetch function called this function and this function is the EMR function.
So these are the
that takes care of the interpolation for the initial at the time initial. But and he every time is just call the every time. But in here at the time this is the time we find the that time you need two functions for the interpolation. Fill fetch and fetch back two levels. That functions take care of.
Fill fetch two levels will fill two consecutive levels.
Fill fetch levels means if we working on the base level, that time I give you boundary. Sorry, boundary. Host cells. Host cells are base level.
So that will contain interface between level 0 and level 1.
No, only at the base level. This function is only base level.
Only at the base level. Yeah, okay.
And this function is working in the high level. Will fetch levels.
And advanced fire at all levels means that
That is our code.
this is your code.
This is the science. I can just call and this regret function is
You will clearly see it. Look at level L minus 1. Sorry, L and L minus 1. This gets embedded. The moment you have a path that's buried in there. Now you have to make that. Clean it. Then go. Every time you have that buried one. So it's like look at this. How level you go? Buried in the intermediate one. Then do. Now once come down, you have patches of those. Wherever refinements were there. Now you have to clean up. Before you go right. Something we understand.
This I our simulation. What I implemented AMR for GP formulation. That is my initial gate. That is my base gate. We not using AMR.
For you. This is course. It's too short. Like what you wanted to try. How much?
What change will be there in the code?
Don't take it. करके बात करेंगे, करके discuss करेंगे. So that probably that's the most useful. This one. This is just learning effect. Therefore, probably that is the one which will take us a long way.
For the AMR, here I use 128. 128. But we're not using AMR. We use 256. That is the AMR. Here I fill the initial value, the base level. This is my base level. With the initial level. Value of 5. That is 0. Now, according to this value, gradient of this, the next level is refined. Just mark these 4 boxes.
It is essentially refining in the region that is all there. It is
There is obviously you don't want to spend time.
so basically it's a wise way of doing it.
Next step, I fill Now, next, at the time of degree, what happened? Initially, I implemented all high values. Then we realized we just implemented around
What have
change. That's why we take the gradient. We can just refine.
Whichever is within that tolerance.
It's initially.
that's so. This will work fantastic. Go ahead.
In this reason also not competition neither.
उधर कुछ नहीं competition नहीं हो रहा है.
वो व्यू के लिए करेंगे बहुत फायदा होगा बोल रहे हैं.
So that's why
काम करेगा.
Can I just include outline?
Very good.
You understand. Right.
Very nice.
Now this is the time comparison.
हाँ ब्रेक ऑलरेडी हो गया है. क्या हो जाएगा पता नहीं.
Here I choose fine gate size 5. Very cross 5.
Good.
Time fix up to 0 to this. Number of series are 30. If I use 0 level, the computation time is 180 in this. I use 1 level without time step. Without cycling. Then I 78, 80, 82 or 80. And if I use the cycle.
Excellent. So I think our aim should be 2000 plus 2000 plus 2000 simulation 3D with this adaptive. Okay, this is our aim. Okay, our aim is 2000 cube simulation of the same day, right, with adaptive grading in the view field.
2000
plus 2000 plus 2000
in 3D.
in 3D with adaptive grading. Yeah, the target was there.
I implemented it already, but after 1005.
नहीं वो with the mu field mu you had that infill with the 30 Kelvin undercooling, no? The one you will use that. You'll get beautiful side arms.
Also, for this reason, in hands-on session.
Yes, you will do this.
Okay, thank you.
The drop here, we should keep it the glossary. So that from the manual ones, what you don't know was